In 1963, a 21-year-old physicist named Stephen Hawking was diagnosed with a rare neuromuscular disorder called amyotrophic lateral sclerosis, or ALS. Gradually, he lost the ability to walk, use his hands, move his face, and even swallow. But throughout it all, he retained his incredible intellect, and in the more than 50 years that followed, Hawking became one of history's most accomplished and famous physicists. However, his condition went uncured and he passed away in 2018, at the age of 76. Decades after his diagnosis, ALS still ranks as one of the most complex, mysterious, and devastating diseases to affect humankind. Also called motor neuron disease and Lou Gehrig's disease, ALS affects about 2 out of every 100,000 people worldwide. When a person has ALS, their motor neurons, the cells responsible for the all-voluntary muscle control in the body, lose function and die. No one knows exactly why or how these cells die, and that's part of what makes ALS so hard to treat. In about 90% of cases, the disease arises suddenly with no apparent cause. The remaining 10% of cases are hereditary, where a mother or father with ALS passes on a mutated gene to their child. The symptoms typically first appear after age 40, but in some rare cases like Hawking's, ALS starts earlier in life. Hawking's case was also a medical marvel because of how long he lived with ALS. After diagnosis, most people with the disease live between 2 to 5 years before ALS leads to respiratory problems that usually cause death. What wasn't unusual in Hawking's case was that his ability to learn, think, and perceive with his senses remained intact. Most people with ALS do not experience impaired cognition. With so much at stake for the 120,000 people who are diagnosed with ALS annually, curing the disease has become one of our most important scientific and medical challenges. Despite the many unknowns, we do have some insight into how ALS impacts the neuromuscular system. ALS affects 2 types of nerve cells called the upper and lower motor neurons. In a healthy body, the upper motor neurons, which sit in the brain's cortex, transmit messages from the brain to the lower motor neurons situated in the spinal cord. Those neurons then transmit the message into muscle fibers, which contract or relax in response, resulting in motion. Every voluntary move we make occurs because of messages transmitted along this pathway. But when motor neurons degenerate in ALS, their ability to transfer messages is disrupted, and that vital signaling system is thrown into chaos. Without their regular cues, the muscles waste away. Precisely what makes the motor neuron degenerate is the prevailing mystery of ALS. In hereditary cases, parents pass genetic mutations onto their children. Even then, ALS involves multiple genes with multiple possible impacts on motor neurons, making the precise triggers hard to pinpoint. When ALS arises sporadically, the list of possible causes grows. Toxins, viruses, lifestyle, or other environmental factors may all play roles. And because there are so many elements involved, there's currently no single test that can determine whether someone has ALS. Nevertheless, our hypotheses on the causes are developing. One prevailing idea is that certain proteins inside the motor neurons aren't folding correctly and are instead forming clumps. The misfolded proteins and clumps may spread from cell to cell. This could be clogging up normal cellular processes like energy and protein production, which keep cells alive. We've also learned that along with motor neurons and muscle fibers, ALS could involve other cell types. ALS patients typically have inflammation in their brains and spinal cords. Defective immune cells may also play a role in killing motor neurons. And ALS seems to change the behavior of specific cells that provide support for the neurons. These factors highlight the disease's complexity, but they may also give a fuller understanding of how it works, opening up new avenues for treatment. And while that may be gradual, we are making progress all the time. We're currently developing new drugs, new stem cell therapies to repair damaged cells, and new gene therapies to slow the advancement of the disease. With our growing arsenal of knowledge, we look forward to discoveries that can change the future for people living with ALS.
The human brain is one of our largest and most complex organs, and for good reason. It's made up of over 100 billion nerves, which communicates in trillions of connections known as synapses. Every action we take or thought we conjure up originates from the brain, and its mastery over our sensory organs makes it arguably the most important organ in the human body. Mainly, patients will be able to move his wheelchair by thinking. Our app will be connected with the EEG sensor that detects patients' brainwaves. Brainwaves can be used to store patients' mood and some health information. It can also be used as an input to Arduino board that controls motors that move the chair. Detected brainwaves can also tell us that patient is blinking. We will use patient's eye blinking to enable him to select any item in our app. We will use patient's eye blinking to enable him to type. Product that will completely change the lives of its stakeholders. Convenient wheelchairs require patients to be escorted by someone to move. Our product allows patients to move on their own. Not only that, but he can also communicate with the rest of the world by writing and making emergency calls and express their opinions and feelings like healthy people.
Brain-computer interfaces or BCIs may currently be either input or output devices. Input BCI is comprised of sensors which acquire electrical brainwave signals together with processing hardware that extract distinct features and translate them into useful commands. The other way around output BCI is translate digital information into electrical signals, but feed into the user's brain power electrodes array or the other simulator hardware. BCIs may be constructed using one of two approaches. The first is non-invasive and may employ electroencephalography or EEG to acquire brainwave signals from sensors positioned on the outside of the skull. Alternatively, non-invasive BCIs may feed electrical signals into brain using a TMS or transcranial magnetic simulation device. The second way to build a BCI is invasive and currently requires surgery to position sensors or simulators inside the skull. Two output technologies have so far been trialed with the first now electrocardiography or ACOG, placing a strip or grid of electrodes on the surface of the brain. Alternatively, intracortical microelectrodes can be implanted a few millimeters into the brain where they may serve as either sensors or simulators. For obvious reasons, today most BCI research is non-invasive. This limits its scope and application, but even so, some interesting results have been achieved. Perhaps most notably, many researchers have used EEG to acquire so-termed P300 brainwaves, which are then processed to allow a user to input letters or commands into a computer. Such interfaces are painstakingly slow, but without doubt they can work. Researchers at University of Washington have been even used non-invasive BCI to send commands from one person's brain to another over the internet. Specifically, in a set of experiments in 2014, one test subject wore an EEG skull cap while watching a monitor screen on which a computer game was being displayed. But the fire button was in the hand of the second subject seated half a mile away in another building and who had a TMS coil placed over the brain. To shoot down rockets, the first user had to think about pressing the fire button. Brainwave signals were acquired by EEG, processed and transmitted over the internet. In turn, the TMS device induced an electrical pulse into the receiving subject's brain, so causing them to experience visual stimuli and press the fire button. Amazingly, the split-second accuracy required to shoot down rockets was achieved. In fact, across 3 pairs of test subjects, success rate between 25 and 83% was obtained. In time, University of Washington, researchers hope to use BCI to transmit more complex ideas and thoughts from one brain to another. This could even allow for what they call brain tutoring, in which Knowledge is transferred directly from the brain of a teacher to the brain of the student. The team at the University of Washington use highly sophisticated sensors, simulators, and processing hardware.
For many years, we have been learning how to interface electronic hardware with the human body. Not least since 1982, over 300,000 people have had their hearing restored with a cochlear implant. These features a surgically inserted electrode array that delivered electrical pulses into its host's auditory nerves. The cochlear implant electrode array is connected to a surgically inserted receiver simulator, which receives wireless signals from external sound processor connected to a microphone. Some external sound processors can also receive and transmit audio directly from a computer. So already, some people have a computer feeding sound directly into their auditory nerves. A company called Second Sight is also developing a visual implant. Indeed, since 2011, more than 75% have been fitted with a Second Sight retinal prosthesis system called the August 2. This is implanted on the eye, where its sexy electrode array simulates the retina of somebody who has been blind due to retinitis pigmentosa. Images are fed to implant for an external wall camera which is connected to a visual processing unit and antenna. The vision so provided is very rudimentary, but does allow patients to identify shapes and even large letters. Since 2016, Second Sight have also been developing a visual cortical prosthesis called Iron 1. This tiny electrode array is implanted into the visual cortex of the patient's brain, so bypassing their eyeball and optic nerves. In January 2018, the first Iron 1 was implanted into a test patient like the August 2. The Iron 1 implant receives signals from an external video camera and currently allows its users to perceive patterns of light. Another developer of brain implant technology is BrainGate. The first BrainGate neural interface system was created in 2002 by Brown University's spin-off company called Cyberkinetics. By 2008, the hardware had been upgraded to BrainGate 2 and was being developed by academics from 5 universities, supported by a score of institutions and foundations. The BrainGate 2 implant is a 4mm array of 100 electrodes that's surgically implanted. A decoder processes signals from the implant, and in turn it allows the user to control an external electrical device. In 2008, a team from the University of Pittsburgh implanted a BrainGate sensor into the motor cortex of a monkey. Over the time, the monkey then learned to feed itself by using its brain to control a robot arm. In May 2012, a team from Brown University implanted BrainGate electrode arrays into 2 paralyzed human patients. One of these was a 58-year-old woman who learned how to use a robot arm to pick up a bottle of water, raise it to her mouth, and take a drink. Clearly, today BCI implants like the Orion 1 and the BrainGate 2 are being developed to assist people with medical conditions, but have robbed them of sight or mobility. Nevertheless, the possibility has to exist for more advanced forms of such technology to develop into sophisticated non-medical human-computer interfaces.